Good evening, everyone. I'm Tom Jackson. We're here at Jackson Systems Training Facility, and we want to welcome everyone that's both here in person and online. And tonight we're real excited. We've got Honeywell Homes by Resideo with us, and we're going to be talking about a product that Jackson Systems has recently brought in and starting to offer to our contractors, and that is the Hydronics product from Honeywell Homes, or Resideo as they're known now. And with me, I've got Mr. Chris Parks?
Absolutely.
Sparks, whatever. Chris Parks. So welcome. Thank you very much.
Thank you.
And tell us a little bit about yourself.
I've been in the hydronic heating and plumbing industry for roughly 15 years.
Awesome.
I've been with Honeywell / now Resideo for about the past 3 years. So excited to be here, be a part of the conversation with you guys tonight. And yeah, going to be covering hydronic heating materials.
All right. So we're really excited. I know you're an expert in this, and we're anxious to be educated ourselves. So without any further ado, I'll turn it over to you and look forward to. The other thing I forgot to mention is for those of you that are watching online, please submit your questions online. We'll read those and make sure we get those up here to Chris to answer for you. There's a little box on your browser there. Just type that in, and we'll make sure we get that question asked, and you can respond, and we'll keep everybody in the loop that way as well. So
perfect.
All righty. Thank you.
Thank you very much. So guys, thank you for attending. I appreciate the logins and the people that came in person. So what I'm going to do is just kind of give a slightly detailed dive into the hydronic heating products, as well as some sizing and selection information. So the first thing I just wanted to touch on briefly is who we are today. So I think everybody is familiar with the Honeywell brand name that we have. Today we're Honeywell Homes by Resideo. What that means is we spun off from Honeywell roughly in October, started a brand new publicly traded company. But what I want you all to rest assured is that we're still the same people selling the same products manufactured in the same spaces. But what we do have is we've got an influx of focus on certain products. We have a lot of new materials coming out in both not only the HVAC world, but also security, plumbing, and hydronics. So it's a really exciting time to be a part of the company and be a part of Honeywell Homes. So what I am going to touch on today is a lot of our hydronic products. So we as Honeywell Homes we manufacture pretty much everything in the mechanical room. Now we don't do boilers, although we do the gas valve, Aqua stats, and some of the OEM components inside of them. But we don't manufacture the boilers. We also don't manufacture any of the heat emitters. So no PEX, no radiators, no baseboard. But almost everything else in the mechanical room, you can get with our name on it. So what I'm going to try to cover today, fill valves and backflows, air elimination, not pertaining just to air vents, but also air separators and purgers. We've got expansion tanks, circulators / pumps. I got flow controls, zone valves, as well as mixing controls, relay panels, and going to touch on some thermostats and wiring examples towards the end as well. So to start off, I'm going to start with the mechanical room and then branch out into controls. One of the products that we have started doing is a packaged system with air eliminators, fill valves, backflows, and expansion tanks. We started doing this because this is needed in virtually every single hydronic heating system that's not filled with glycol. When we break that down and start looking at some of the individual components that are inside of there, we've got 2 different fill valve and backflow devices available today. One of these is relatively new. We just launched it towards the beginning of last heating season. And that's going to be our NK300S. But first, I'm going to talk about our existing fill valve and backflow. So with this product, you get a simplistic double check with an atmospheric vent. So you've got 2 check valves inside of here, and you have a little vent drain that needs to be plumbed out. What happens is if any one of these check valves ever fails, you're going to get water leaking back down to the drain. This prevents any of your hydronic heating water that's been sitting stagnant in the lines for, could be 5, 10, 15 years, from ever making its way back into the drinking water supply. And then we also have a fill valve, which are typically married together, although some people will put a bypass around here for faster filling. Our fill valve, all of this is going to be 1/2 inch, but what we do on the top is we design it with what we call a dial set. So at the very top of our fill valve, you've got a little gauge here that's going to show you what the pressure rating is. So we come factory set at 15 psi. The old industry standard used to be 12 psi. We've raised that because we've seen more and more condensing modulating and condensing boilers coming out. And what's happened with that is typically they need slightly higher pressures than we used to see with the old 12-pound guys that we used on cast iron and copper fin boilers. We also ship it with a gauge port, so you can take this plug out, add a pressure gauge, and you can see your pressure at the point of source. So you hook this valve up, and you're basically setting your pressure. Your incoming pressure could be at 60, 80, whatever it is. You're going to reduce it down to 15 psi. And I'm going to talk about a little bit of the sizing and what that means and why we select those pressures here in a little bit. But the other thing I want to show you on this is at the very bottom, we have a shutoff valve. So one of the things I always recommend on a hydronic heating system, once you have filled that system and you've let that run through the air eliminator, which I'll go over in a little bit, shut your water makeup off. The reason I say that is you will get some residual air that will purge out down the road. And what that's going to do is anytime you purge out air, you're basically dropping a little bit of pressure out. But a lot of times it's minuscule. What I've seen happen a lot of times is I guess you could say eventually major problems where you're masking an issue. Could be a nail that's the drywaller hit in some tubing that erodes over time. You end up with a small leak. This will continue to keep your system pressurized at, in this instance, 15 psi. If you do that, you may be masking a bigger problem. So I always recommend shutting off your water makeup to the system after you've had it commissioned for a while. Also, by code, this vent needs to be run to a drain. If you do run into an instance where one of these check valves fails, you're going to end up with water gushing all over the place. So make sure you run that to a drain with an air gap. We also ship it with this little plastic cap. Once you're done, you can put that on there. The reason we do that is homeowners love to twist anything that has numbers showing on it. We don't want anybody coming through and adjusting this because typically on a residential boiler, you're going to have your relief valve set at roughly 30 pounds. If a homeowner comes in and adjusts this up to 20 or 25 thinking it's going to make their heating system better, you're eventually going to run into a situation where you're going to be bleeding out of the relief valve. So we basically give you something to hide the dial set so that the homeowner doesn't really know what that's for. What we've done recently is we brought over one of our valves from Europe. This is our NK300S. And what this does is we ship it. It's basically an upgrade to the valve I just showed you. So what this is going to do is it includes a pressure gauge with it, whereas it was an option that had to be field installed on the previous one. We ship it with 2 isolation valves on here. The reason we do that is because this valve is completely serviceable. It's pretty unique in the industry. I'm not aware of anybody else that has one that can be completely serviced. Sediment is usually one of the killers in our previous valve that I showed you. So what you can do with this is you can take every bit of it apart. So inside this one piece of cast body, you've got your first check assembly, which is housed inside of here. I'm sorry, I'm looking at it backwards. It's housed inside of here. You have your second check assembly housed inside of here. And then you have your PRV cartridge down here at the bottom. Every bit of this can be taken apart, cleaned, and serviced. As an example, when we take this out, and that doesn't come that loose, I have previously loosened this. So here's our first check assembly, which can be completely cleaned and scrubbed, because sediment will get in here from time to time and kind of plug this stuff up. One of the big things, you also have access to the sediment screen. So we went with a much finer mesh because we've got bigger surface area on here. So what you're looking at with this is a 200 micron sediment screen. We made a rolling change from the industry standard of roughly 500 micron, and that eliminated a lot of the problems that we were getting with sediment coming in and kind of trapping the valve open. But it's nice to be able to take this all apart without having to run and replace it and hope you can get threads matching back up again. The PRV down here on the bottom, just as a setup installation, it ships with this little plastic adjustment tool out of the box. As I had kind of mentioned with the previous cap, homeowners love to play with things that move. So you can use this to set your initial pressure rating, which this is set at 15 pounds, but you'll be adjusting that when you fill it. Afterwards, throw this thing away, keep it in your truck, do something with it. And then here on the bottom, where you make your pressure adjustment, you can use just a standard flathead screwdriver to get in there and make the adjustment. So this is great on initial install. I would not keep it in there. And it also ships with this plastic housing. This comes this way from Europe, from our European division. What you're going to want to do is you have the option of either using this or not using this. This isn't just packing material. This is actually engineered to plug together and be one solid block against the wall. It also can be operated either way. Just make sure you follow the direction of flow. And we make it in several different connection types. So our most common is just sweat and thread on this. So it ships with both sweat and threaded tail pieces in the box. But we also offer a version with press. We've been doing more and more with press in our mechanical room offering. This is one of the valves right here. We partnered with a major manufacturer on all of our press fittings, so we're not building our own. But you'll see here kind of the press connections on this device. The other thing that I didn't touch on, there's a couple black plastic plugs that are inside of there. Those aren't just for decoration. Those are actually test ports. So what you can do with this is you can take a differential pressure meter or some kind of a backflow test device, and you can actually hook it up to those test plugs that are in there. That gives you the ability to kind of walk up, get a sense for if it's working or not before you start have to take everything away. So I talked on those two different devices. There are applications where you may want to use one or the other. One of the things that we see is certain areas of the country require RPZ testable backflow preventers. We don't have that in our current offering, but we do sell our fill valves separately. So I can take this backflow preventer apart, and you can basically marry that up to this. That'll give you your system. The other thing that I see some people like to do is create a manual bypass with a ball valve so that you can purge incredibly quickly. Our NK300S, since it's one piece of cast brass, has got some big features and benefits. However, one of the drawbacks is you cannot bypass the PRV. So if you want to fast fill, with street pressure, you really have to build a bypass around this by separating these two in our portfolio. So I get asked a lot how to do proper purging, or I get calls where we set up the PRV at 15 pounds, but it's blowing the relief valve, and I think it's because your PRV is leaking through. And I've been out to a lot of those job sites, and I usually see that the issue is not the pressure reducing valve. Could be ours, could be anybody else's, but it's an issue with the purging. So when you go to purge a system, in the first example, I'll show you what we have going on. That's just coming in from the city, going up into the system, kind of going left through the boiler, up around the top as if it was a one-loop system, and then it comes down into a boiler drain with a ball valve right behind it. That way you can close the ball valve, drive that water up around the system, out through the system, through a boiler drain right before it. And you're hitting 95% of the water that's in there. That's a very effective way, but that's not real practical because we don't see a lot of one-zone hydronic heating systems. So this is much more common. And I'm showing a diagram here with 4 pumps. That could just as easily be one pump with 4 zone valves. But in this instance, we're bringing water up, we're going through the system, and we're going to have to go loop by loop. So what you're going to do is you're going to close off, in this example, the 3 zones on the right-hand side, and you're going to purge the first loop. Same type of setup. You've got a ball valve at the bottom with a boiler drain right above it, and you're purging through there. This is where I've seen a lot of people make the mistake and blame the PRV for not working properly. If you close that off while you're filling with city pressure, or say you're purging at 30 pounds, 50 pounds, whatever you're using, you're keeping 30 to 50 pounds in that loop. So if you close that off and then move to the next loop, you have essentially locked that section in at a very high pressure. If you then, over time, open that valve up after you've already filled it, so let's say you go through, you purge every line, then you pressurize it up to 12 pounds. If that system, if that valve and that loop opens up, you're now introducing much higher pressure, which will bleed out of the relief valve. So you want to make sure that you're basically trading them off, and you're not locking one loop or one area. Could be closely spaced T's, could be an ejection loop. You don't want to lock anything off because you can lock higher pressure into some of those areas. And then last but not least, I've just got another diagram here. There's so many different ways to plumb a hydronic heating system. I'm just showing a couple different diagrams here. In this instance, you've got a couple different loops coming off of there, different characteristics on the flow rates. So we've got closely spaced tees, so you can drive one flow rate around the boiler and multiple different flow rates in the secondary loops. So in this example, again, just kind of showing you how to purge some of those out so you can get proper movement through there and get all of that. Get everything balanced to the same pressure and get all the air out of there. Now when we talk about sizing the fill valve, so the old industry standard that I had mentioned used to just be 12 pounds. Our expansion tanks are still sized at 12 pounds, which I'll show in a minute. But 12 pounds was based on the average home that was installed whenever they made that decision. So what you're looking at is, in our hydronic heating world, we typically use PSI for the static pressure, and then we measure our pumps in feet of head. So if you're looking at this, 1 foot of head is equivalent to 2.31 feet of, 1 PSI is equal to 2.31 feet of head. That's a formula you're going to want to know and understand because that comes up in our world a lot. So with this being said, in this example, that 12 PSI, so let's say we've got the boiler down in a basement, we set it at 12 PSI. What that's going to do is give us the equivalent pressure of stagnant pressure at the top of 27 feet. So that means you will still have pressure at roughly 27 feet tall. So what do you do if the building's taller than 27 feet? You increase your pressure down at the basement. So if you were to increase that to, say, 15 PSI, that's now going to give you the equivalent, I've already done the math here, but that's going to give you the equivalent of being able to handle the capacity of roughly a 35-foot tall building. So the one thing to keep in mind, your pressure, you're working with gravity when it comes to static pressure. And I think we have a question from the audience.
Yeah, from Paul in Denver, Colorado, Sun Chasers. He wanted to know, where is all the Honeywell product manufactured?
It's a good question. A couple different places. So a lot of our products are made either in Maasbach, Germany. So like our NK300S is Maasbach, Germany. Our fill valve and backflow is Maasbach, Germany. Some of our products are actually made in the US. So our air eliminators, for example, are manufactured here in the US. So it just kind of depends. We have stuff made and sourced from different areas. Some of our zone valve heads actually come from Hungary. So it depends on which product we're looking at. But typically everywhere, I believe, to the best of my knowledge, everything that we manufacture is a Buy America compatible country. Good question. So anyways, with the pressure, you basically just need to make sure you've got the capacity down at the basement to handle that. So when we look at this, let's say we've got a really tall building, something to keep in mind, and this isn't real common in residential systems, but sometimes in light commercial jobs. If the boiler is in the basement, you may have to set that pressure incredibly high to be able to get the capacity of height. So you'll have pressure at the top. It could be a radiator, in-floor heating, whatever it is. So what you can do is you need to keep an eye on the relief valve setting on the boiler. Always give yourself a little bit of cushion. A lot of boilers do have the capacity to go with a higher pressure relief valve. So you may have to adjust that relief valve from a 30-pound to a 50-pound. But always check the manufacturer's ratings on your boiler. So the other component, we talked about filling it with a certain pressure. We talked about backflow devices. Let's talk about expansion tanks. The purpose of an expansion tank is essentially to keep consistent pressure in your system. As hot water, or as water gets hot, it's going to expand. So when we look at expansion tanks, the current hydronic expansion tanks that we sell today are not actually filled with air, per se. There's basically just a welded tank that's got a little diaphragm lip across the top, and that's going to be pre-charged with a certain pressure. So that's going to be pre-charged to, say, 12 PSI, because again, that used to be what we saw all the time. As your system increases, it's going to create back pressure. So you want to match your expansion tank to the same pressure you're going to be running for static pressure in the system. And I think we have a question.
We do. They ask, why do you have the air vent valve on the supply side and not in the return side with the expansion tank and fill valve?
I think he's referring to this diagram. Whoop, got away from me here. I think in this diagram, I pulled these schematics from the HPAC magazine. There's a little note there I couldn't really read as far as why that's set up. I don't normally recommend having it that way, and we'll talk about circulator placement, but typically you want to put, as it's shown in the first and third drawing, this thing gets away from me. Usually what you want to have is your water makeup coming in. You typically, there's different ways to do it, but typically it's teed into the line between the expansion tank and air eliminator, and then your pump is always on the discharge of that. You never want to pump into the expansion tank. But there's different placements. Sometimes mechanical rooms don't permit for the perfect schematic that you see here on some of these. I'm not sure if that answered the question or not.
I think so.
And then on the expansion tanks, so everything's kind of sized for 1/2 inch on your water makeup in a hydronic heating system. If you get an expansion tank that's 3/4 inch, more than likely that's a domestic potable water expansion tank and not a hydronic heating expansion tank. The diaphragms are different between the two of them. So in a hydronic expansion tank, we use Buttle and EPDM diaphragms that have 1/2 inch male connections on the top. So if you look at our air eliminators, you're going to see 1/2 inch female connections on the bottom. Expansion tanks are 1/2 inch male connections on the top. And all of our fill valves are going to be 1/2 inch. Always try to match these to the configuration of your static pressure. So we just talked about that. So let's say in this example that we're coming to 15 psi for the system that we want to run. Before you hook the expansion tank up, you want there's a little Schrader valve on the bottom of it. You want to pressurize that to 15 psi. The other thing that I will caution you on, I've been on job sites that get commissioned when it's -30 outside. Make sure you pressurize that in the conditioned temperature you're going to be operating in. Because if you try to pump that thing up at -30, it's not going to be the same pressure when it starts to warm up. So you match the expansion tank to 15 pounds, and then you also want to just hook it in and basically run it at the same pressure. Because you want to balance pressure between the water side and the air side to get full acceptance inside that expansion tank. So there's different expansion tanks out there, and how do you know which one to go with? Because we've got everything from a little 2-gallon all the way up to commercial floor-mounted expansion tanks. The way I recommend is by checking the water volume in your system and going off of, make sure I'm on the right slide here, going off the water volume in your system and comparing that to the water volume capacity at varying temperatures in your system. So in this chart that I have here, I've got a couple of examples. On the left-hand side, what we're looking at is the acceptance volume of our common, call it residential expansion tanks. And we can get this for the bigger ones as well, but this is the majority of what we sell. So when you're looking at that, the Model 30, which is a 4.4 gallon, is our most common expansion tank by far. So with the Model 30, what you want to do is on the left-hand side of that column, trace down and find the temperature, the maximum temperature that your system will be operating at. So if we're doing an in-floor heating system, let's just say that's going to be roughly 120 degrees. So at 120 degrees, the Model 30 expansion tank can handle the capacity, I'm trying to read off my screen, of roughly 158 gallons of water. So what you can do is just start adding up where your water is. So on the right-hand side, I've put the water volume per lineal foot of different types of piping. So I've got copper, both type L and type M, as well as PEX, Pexal PEX or PEX aluminum PEX, and just get a rough idea of where you fall. You don't have to be incredibly exacting because my mantra on the expansion tanks is if you're anywhere near the maximum capacity, go to the next size up. Expansion tanks don't hurt going larger in size. So if there's any question, always go larger. And we have another question from the audience.
Couple questions. First is from Bruce at AirServe of Mid-Michigan. He asked, which direction should it be mounted, up or down?
We have varying answers. That's a great question. Should the expansion tank be mounted up or down? I've always seen it mounted down. Now, with that being said, I don't think it really matters. And the reason I say that is it's nothing more than a diaphragmed air tank. So your expansion, regardless of which way it's oriented, is going to be pushing against that air bladder. The reason that you'll see it always mounted down in the installation manuals is because of that Schrader valve. So if you ever have to bleed water off, you always want to bleed water towards the floor instead of towards the ceiling, against the wall, etc. But we always show it down. In practicality, it really doesn't matter. But great question.
All right, and we got one more question from Ricardo at UEI College. What do you pressurize the expansion tank with, air or some sort of chemical?
Air. Yeah, good question. It's just it's just basically air being used as the buffer. So usually, well, I should say always do air, because even if you put something else in there, my concern would be that it might damage that diaphragm. The other thing is, one of the good checks to see if the expansion tank is busted or not, you can either go up and knock on it. If it sounds hollow, you're good. The other thing you can do is go to the very bottom of it with the expansion tank and just kind of push against it like you would on, say, a car tire. If water starts spraying out, your diaphragm's busted. There should be no water in there. But I'll caution you, if you use that as a check, you're letting air out. So if there's nothing wrong with the expansion tank, you have now let air out of the expansion tank. The only way you can ever get that thing back to where you want it is to disconnect it from the system and pressurize it with no water pressure on the other side. So check to see if, knock against it and see if it's hollow first, because as soon as you press against that relief valve, you're letting air out of the back side of that. And then on the expansion tanks, so was that all the questions that we had for now? Okay. So on the expansion tanks, when it comes to sizing, this is my preferred method. And you know how much PEX you bought. If it's radiators, baseboard, you know how much copper is run to them and how much is in there. So everything will have a water capacity on it. Your boiler will have a water capacity size. Your boiler piping will have something there. But just kind of add it all up, ballpark it, see where you're at, and that'll give you an idea. Always go larger if in doubt. So if you're not good at math, or let's say you're walking into a system that's existing, you're getting relief valve, you're getting pressures bouncing up and down. I have some general rule of thumbs that have been published that go through a couple different situations. These are very safe numbers. Typically, these are grossly overstated, but it's something you can at least look off of. So if you know how many BTUs the boiler is, look at the output rating of boiler, not the input, and then look at what's being used. So is it fin tube, baseboard, radiators, etc. Where this has come from is the average temperatures that are used in those types of radiators or baseboard or heat emitters, as well as what's the average water volume inside of them. So you can use this based on what's doing the heating, as well as what's the output of the boiler. I've also got another chart to the right that shows you what you can use based on estimations of PEX tubing. So both of these charts can be used if you don't want to add it up, but my advice is always to add up the water volume, at least get a rough gauge of where you are, because that'll let you know, are you close to the size, should you go up to the next one, etc. We also have Sme expansion tanks. If it's a commercial job, it adds about $1,000 right off the top to the price. But if you need commercial expansion tanks, we have those as well. The other piece, so we've talked about 2 of the 3 things that we have in our boiler trim kit. So we've talked about fill valve, backflow, selecting pressure, expansion tank. The other critical piece is going to be air elimination. There's 2 different types of air separators. We sell both of them. You're looking at an air purger, also referred to commonly as an air scoop. We also sell a super vent, which is a microbubble air eliminator. There's 2 major differences, both in price and functionality, between these 2 different types of air elimination devices. The first being with an air scoop, it's really nothing more than a big block of cast iron that has a couple of vanes inside of it. So the theory behind this is, as water starts to travel through the piping, it's going to collect and kind of roll up to the top, because air floats. So it's going to roll up to the top, get caught in those vanes, and then purge up through the top through an automatic air vent. These used to be the standard 20, 30 years ago. The reason was we sold cast iron boilers, copper fin boilers, essentially high mass devices that had a lot of water, very big manifolds inside of the heat exchangers. Today, that's not exactly the case. So there's a couple of big drawbacks to this. First, this does not do an effective job of getting rid of the microbubbles. As the water starts to heat up, it really brings those small bubbles out. That's a lot of times where you hear the noise, the gurgling, the noisy pipes, etc., is from the microbubbles. This does a great job of collecting the big water bubbles, but not, or the big air bubbles, but not the micro bubbles. You have to add a third-party air vent. A lot of the air vents, and I'll talk on this in a minute as well, a lot of the automatic air vents are not the best. They last a few years and they start to leak out. So we have some high-capacity ones that are very long-lasting, but you have to add air vents to this, and the installation is kind of critical as well. So you have to have at least 4 times the pipe diameter of straight pipe prior to this. So in tight spaces, these don't work effectively because you can't plumb them in properly. So if you have to come in up 90 over right into this, the problem is your water never gets a chance, or your air never gets a chance to float to the top of the piping and get out. So we recommend at least 18 inches if you can get it of straight pipe prior. At a bare minimum, you want to get at least 4 times the pipe diameter. So if you're talking 1 inch, you want at least 4 inches of straight pipe prior to that air scoop. What we have that I'm showing you now is the super vent. So the super vent is the micro bubble air eliminator. So if you have a modulating condensing boiler, and I mean, in my opinion, really any boiler in today's world, the modulating and condensing boilers have very small waterways through the manifolds inside the heat exchanger. So if you end up with air bubbles inside of there, you can end up with cavitation because that boiler is producing so much heat that it's actually boiling the water because you've got air that's slowing it down. What happens with this is we have a coalescing media, looks like a stainless steel brush inside of it. As the water passes through here, any of those micro bubbles kind of get stuck on those bristles, and they end up purging their way up to the top. What happens is once those micro bubbles start to come up, you've got a big collection area here where they're going to come inside of this device. Inside of here, we have a big plastic float. This is solid all the way throughout. As the air comes in and gets collected, it's going to basically push up here, push this float up to the top. There's a mechanism inside of here that's going to open this up, and it's going to bleed the air out of the tip. This can also be replaced, serviced, etc., but incredibly reliable air vent. The other thing you can do is after you've gone through and done all your purging, you can shut this cap off just in the case that it may leak. But these are incredibly reliable. We redesigned the tip of this roughly 10, 15 years ago. It used to vent vertical. We did have problems with those leaking years ago, especially on glycol systems. For those of you that use glycol, you know it has a way of finding leak paths that water doesn't. So with this, when we redesign this head and the guts inside of here, it doesn't matter if you're using glycol or water. We don't have issues with these leaking anymore. Every now and then it's possible, especially with glycol, because it can be sticky, especially around air. It is possible for that float to get stuck inside of there, but that's as simple as taking this apart, cleaning this off with fresh water, and putting it back together. And then off the bottom, I was talking about hooking everything up with half-inch. We have half-inch connections here at the bottom. Typically, you have a half-inch pipe coming down, an expansion tank hanging here, and your water makeup coming from either side. And I think we've got a question from the audience.
We do, from Constantino again. He wants to know, can you use the super vent on chill water systems?
Yes. Yes, it's fine. I can't remember the specs on the temperature rating off the top of my head, but I believe it goes down to 40 psi. There's really nothing in there that's going to run into a problem. There's not a whole lot of mechanical parts, but good question. Yeah, we sell them on chiller systems all the time. We also make that in, I should have mentioned the sizes. We go 3/4 inch all the way up to 2 inch. So both sweat and threaded. So depending on the system, 2 inch will get you into a pretty good light commercial job, and that'll work absolutely flawlessly. So capping out air elimination. I can't talk about air elimination without talking about air vents. So we've got a lot of different air vents, and each air vent has a slightly different application and best use. So what I did is I took our portfolio of air vents that we've got and just laid them out in a sheet on this page and kind of listed where they're best used. So the first is I talked about on the super vent that we have. I talked about how we changed the design, made it a 90-degree elbow, and virtually all of our leakage issues went away. We make that same type of design in what we call our super vent top. We've got a 3/8 inch and 1/2 inch vent. These are most commonly used in commonly operated vent areas. So that could be our air scoop, that could be hydraulic separator, but in an area where you're bleeding out a lot of air, like a water main area. We also have an EA series vent. So the EA is a pretty unique vent that we do quite a bit with in certain areas of the country. What makes the EA unique is it has a built-in shutoff valve. So if you have an area where you are having constant failures on air vents, you can put this in and actually shut it off to prevent leaking. When you shut it off, it's actually rebuildable as well. So you can take the top apart, come in with a new one, and replace the whole float assembly without having to drain down any of the system at all. So very unique. We sell a tremendous amount of those in Canada because, as I had mentioned, the main reason being Canada has a really bad habit, or not Canada, glycol has a really bad habit of leaking out where water won't. And in Canada, because of their temperatures, they use a lot of glycol. So that little 1/8-inch EA vent is incredibly popular in Canada because of the ability to shut it off and service it. We have just basic universal vents too, so nothing real fancy, but all of them have a float assembly inside of them. And then we also make a low-profile vent that's good for baseboard, tight applications, areas where you don't have a lot of room. So talking about circulators, I put the word circulators up there instead of pumps. And I did that intentionally. When you're looking at a hydronic heating system, it's not technically a pump because what you're doing is it's a closed loop system. Every bit of pressure that you put into it is going to come back on the opposite end. So it's kind of like a Ferris wheel effect. Pumps are used like sewage ejectors and sump pumps, where you're taking a body of water and you're moving it physically from one location to another. In our world, we're circulating the water. We're literally just putting it up here and then it's coming back to us on the other end. We have a couple of pumps in the residential light commercial line that are 3-speed circulators. A couple of things that make this very unique is this is one of probably the best service pump that's out there. What we've done with it is we have matched it up to the same bolt-to-bolt dimension that you see on anything else in the same horsepower rating. So on our two smaller sizes, it's a 6.5-inch from flange to flange. And on our bigger one, it's 8.5 inches from flange to flange. That is the most common size dimensions that are there. So if you're going and swapping out a pump, this is going to fit in the exact same spot without having to do anything to the piping. The other thing that we have done is you'll notice that there are 4 bolts here. For those of you that do a lot of circulators, you'll know that your pumps are typically 2-bolt flanges. This does not require a special flange. So what we've done is we've actually just created 2 flanges inside of one. So you've got the ability, because when you install a circulator, you have to keep the motor parallel to the ground. You never want to see the motor staring up at the ceiling. You never want to see the motor staring down at the ground. So it's always got to be at least parallel to the ground. So if you're ripping out a pump, let's say we only had 2 bolts here, it is possible you may have to mount the pump like this or unsweat those flanges and reattach it. With ours, it's going to go right in. Doesn't matter what you're replacing, if it's a rotated flange pump or not. Comes with a check valve inside of it as well. And I should show this as well. We've got 3 speeds on every single one of ours. So this is not necessarily industry changing, but we have targeted this as a universal replacement pump. We've got 3 different speeds on every single one of them. It's adjusted right here at the control. So I'm going to go into a little bit of depth talking about sizing, how you come up with which one you should be using, etc. I'm going to show you a couple of the pump curves first. So talking about our 3 different pumps, we have a couple of European measurements that you may or may not have heard in other pump brands before, but we have a 1558, a 2699, and a 4344. Each one of those has different characteristics, and I've got some of the pump curves up here, so you can kind of take a look at them. But they're very common circulators that those 2 numbers are actually European measurements that pertain to flow rate and head pressure, but very commonly spoken in the heating world. So sizing pumps, or circulators as we call them. A couple of things you need to know. You need to know what the BTU load is. In turn, what the gallon per minute flow rate is going to be. what your resistance to flow will be. So in our world, we use feet of head. And then if you're using water or glycol. The water or glycol piece is just because water has more friction as it moves through the pipes than water does. What did I say about it? Oh, I said water and water. Glycol has more resistance than water. Sorry about that. Thank you. Got a correction from the audience. Thank you. So we're going to get into a little bit of math here. And I apologize because all my cheat sheets are down at the ground, so I'm going to be looking down at them. So when you're coming up with flow rate, so let's say you're going into a job site that's got an existing boiler, or you have a rough idea of the area that it's serving. Because we could be doing a pump to serve the entire system with zone valves, or some people prefer to do what's called zone pumping, where you're going to have a pump on every single loop. There's pros and cons to both methods. My goal is to prep you so you can handle anything that you walk into. So when you're looking at the pump and the system, you need to come up with the flow rate first. So in order to come up with the flow rate, it's going to depend on your delta T. Delta T is just change in temperature. In the US, we have pretty much adopted a 20-degree temperature differential. I believe we have done that because the math is incredibly easy. So I'll go over that shortcut here in a minute. But when I was designing systems, a lot of times I would design it for a 30-degree delta T. Part of the reason being, with modulating and condensing boilers, you want to bring the water back to that boiler as cold as possible. So if you did a 30-degree delta T instead of a 20-degree, you typically brought the water back about 5 degrees cooler. It didn't move as fast, but you brought the water back cooler. So if you designed your flow rates, et cetera, to handle that, the colder the water, the better. But a lot of that depends on the system design. So to come up with the formula, if you want to do the math out, you're going to multiply the weight of a gallon of water, which is 8.3, by the number of minutes you have in an hour, which is 60, times the temperature differential you want to use. So in the first example, I'm going to use a 20-degree temperature differential, because remember I said the math is real easy on that one. So what we've got is, let's just say we have a 100,000 BTU boiler that's there. Actually, I'm going to go up. Let's say we've got a 120,000 BTU boiler. You don't need to look at the input rating on the boiler. You need to look at the output rating, because that's how much energy is actually being produced. So if you look at that boiler that's in there, let's just say hypothetically the output is going to be 100,000 BTUs. If you divide it by 8.3 times 60 times 20, you're going to come up with 10 gallons a minute. If I change that to a 30-degree temperature differential, which I was mentioning I like to do on my system designs when I was doing in-floor heating systems, you're multiplying it by a bigger number down at the bottom, which brings your slow rate slower. So it makes sense, right? You move the water slower, it's going to have a bigger temperature change by the time it gets back to us. So if it leaves at 130, it's coming back at 100 versus leaving at 130 and coming back at 110. But that can mean you can use a much smaller pump. The shortcut, if you're doing some stuff quick, just take the output and divide by 10,000. That's our 20-degree delta T. So when you take 8.3 times 60 times 20, it's 10,000. So if you've got a 100,000 BTU boiler output, 10 gallons a minute. In this example, 40,000 BTU output divided by 10,000, 4 gallons a minute. So you can immediately walk up to a system now. You can look at the output rating on the boiler, assuming it was sized properly, and look at the max capacity that boiler should ever need for flow rate. Now, there's some other things you got to take in mind with that. You got to make sure that you're not eroded, your pipe sizing is correct, and there's other things going on. But as far as pump sizing, you've now got an idea real quick off the flow rate. So that's if you're doing one pump for everything, or one pump for the boiler. So what if we're doing a pump for the system? So let's say we've got a zone pump that's feeding an area that's, I don't know, let's say 1,000 BT or 1,000 square feet. If you have, every market's going to be different, every house is a little different, but if you did a rough heat loss calculation, let's just say on average it's going to need 20 BTUs per square foot, relatively new construction. So 1,000 times 20, you're going to have 20,000 BTUs. Divide that by 10,000, that pump needs 2 gallons per minute. And I don't have that math up there. I just did that one off the cuff. But you can basically get a rough idea for how big is the space that's being heated with that zone pump, and just divide that by 10,000, and there's your flow rate. So I'm going to jump backwards real fast. I'm going to jump around to my slides to the pump curves again. So when we looked at the pump curves, there's always two sides you got to look at. You've got the x-axis and the y-axis. So you've got flow rate listed on one of them. You've got pressure on the other. So we just came up with the flow rate. So if we were to trace the number, we kind of know where we got to look on that. But now we got to come up with the pressure to identify really where we need to be and which pump and which speed we need to run it on. So when we calculate the pressure drop, you need to calculate it based on the capabilities of the worst case scenario. So if we are looking at gallons per minute, let's say we're sizing a central pump. I'm going to use the example of one pump with multiple zone valves. That pump has to be capable of delivering the flow to every single zone in the system. So again, let's say it's a 100,000 BTU boiler. It's got to be capable of driving 10 gallons a minute on a 20-degree temperature differential. We need that pressure rating to really identify the pump. So what we need to do is figure out where the water is going. Water always takes the path of least resistance, but we need to figure out which is the worst resistance, and that's what that pump has to be capable of delivering. So in order to do that, what I usually do is go through and break out where is the water traveling from and to. So I'm leaving the boiler. I've got to get through the boiler piping. I've got to get through the supply and return piping to that manifold. And then we could have 4 loops on that manifold, so which of those 4 loops is going to be the longest? That's the quickest and easiest way to do it. So I've got an example down here, and you can come up with pressure loss charts all over the place. So there's an engineering toolbox on the internet that has pressure loss at varying flow rates. Uponor, a big PEX manufacturer, has got all their flow rates listed, or their pressure charts listed. And I've got an example here on the right for half-inch PEX, because that's probably the most common when we're looking at in-floor heating systems. So in this example, we're running the system, I believe, at, I went through on boiler piping, did 1.25 inch pipe, 9 gallons a minute. I did system return pipe, so that 9-gallon system has multiple zones. So the first zone that we're going through, we're driving 2.2 gallons a minute through it. Then we got to go through a zone valve, and I'll talk about zone valve and coefficients of velocity too. But we're going through a zone valve, and then we've got the longest loop. So we're basically tracing everywhere that water's going and the pressure loss through every segment of it. So in this example, I kind of totalized everything and put some examples of footages of pipe and distances of pipe and added up all of our head loss. So in the boiler piping, 1.25 inch, 0.02 feet of head. Supply and return piping, so 3/4 inch running 120 feet. So that's supply and return because the water has to get back to you. We're looking at 2.65 feet ahead. The zone valve at 2.2 gallons a minute is 0.91. And then we've got the longest radiant loop, which is only 1.29 because that loop is only doing 0.6 gallons a minute. So your system designs will kind of tell you where you need to be, but we're breaking it down. So that system, again, we're looking 9 gallons a minute on the flow rate. We're looking 4.87 feet ahead. So very, very simplistic system. And when we place that, you basically just summarize it all there. You got your flow rate and your head pressure. You place a dot on the pump curve. You need to go to the curve that's above the pump curve. So where we've got that red dot, that's basically where the system needs to operate. As we're operating and running, what's going to happen is there's actually an operational curve that tracks that. It's kind of looks exactly like a pump curve but flipped on top of each other. So what's going to happen is that pump's going to operate roughly at 10 gallons a minute at 6 feet ahead because there's a pressure curve that it follows. So as far as sizing a pump, you just kind of find the pump that closest fits the duty point that you come up with for the system. I'll pause there for 1 second to see if we have any questions. It's a lot of math real fast. So sorry it's late, and I apologize for giving you the math.
What happens if you make the wrong selection of 1, 2, or 3? Just doesn't perform as well?
Good question. If you don't make the right selection on the pump on 1, 2, and 3, you go to a bigger pump. Most of the pumps in that residential line are going to match up to pretty much the same bolt dimension. So you just slap a bigger pump in there. But what you'll see is you're going to run a different realistically, what happens is if you're close and it's a little bit off, so we size that for a 20-degree delta T. What will happen is you won't get a 20-degree temperature differential. So maybe you're going to get 23-degree temperature differential. It's pretty minuscule, and 99.9% of the time, the numbers you're running are overstated anyways. So there's a lot of cushion built into everything when you're doing that as well. Great question, though. So we kind of talked about this being a universal replacement pump. So what we've done is we have put together a cross-reference sheet that lists a lot of the major manufacturers that are out there, what pumps exist, and what these 3 pumps will replace. So this is available at Jackson Systems. They have copies of this both digitally and printed. So if in doubt, if you walk up to a pump, just read the rating plate off of it and they can help get you into the correct one. That's the easiest way to do the pump sizing, is to basically find out what's in there and just replace it with the same thing, with ours, of course. So
We do have another question,
all right.
and I'm sure I'm mispronouncing his name. It's Lalo. He asked, are there tools, apps, or sites that can help with the selection? That may be just what you covered there.
Yeah, we don't have a website that's live on pump selection, but as far as product availability, product information, we have the cross-reference sheets, we have pump curves, and then we have a technical line that can be called in as well.
Okay. And then another question from Ricardo at UEI. Are those pumps single-phase or 3-phase?
These are all going to be single-phase 120-volt circulators. Good question. Yeah, these are all small pumps, so when you break it down and look at the horsepower rating, the smallest one, which is most common, and I'm talking mainly about residential systems, this one is a 125th horsepower. So very, very small. The amp draw on speed 1, I believe, is 0.35 amps, like 35 watts. So these are all going to be 120-volt single-phase. Okay, so we talked about pumps. There is the capability of zone pumping, so putting a pump on every single zone. The other thing that we like to see, well, I'm more of a fan of zone valving, truthfully, but again, there's pros and cons, and I could argue that till I'm blue in the face on which one's better. But with zone valves, you get the ability to run one circulator, and these valves draw very, very little power. So what these are, zone valves, just from a top-level standpoint, are normally closed water valves. So they have a spring inside of them that keeps them shut. You give it 24-volt power on a call for heat, and it opens them up. So unlike a pump where you throw 120 volts to it and it starts basically running, with a valve, you just give it 24 volts, it opens up, and you use a third-party control. I'll show you our controls later, that tells it to open, and then you get flow through to the system. And we have a question. Yes?
Joseph Holland, he asks, do you offer an ECM motor on your pumps?
Not today.
Ah.
Not to be expanded on yet. Not today. ECM motors, electronically controlled motors, pretty much all that's ever installed in Europe anymore today because they draw much less energy. They also, most of them have the capabilities of automatically ramping up or ramping down to fit the needs of the system. Different ways to control it. You can do it through pressure differential, temperature differential, but today all of ours are going to be fixed speed circulators, which are selectable with 3 curves. But it doesn't ours don't even automatically adjust between those 3. It's just you pretty much select it on the commissioning of the device. Maybe adjust it if you want tighter or wider delta T. But ECM pumps are growing in popularity. We don't have one today. Okay, so zone valves. So we have been in the zone valve market for a very, very, very long time. If there's one thing I think Honeywell is known for on the hydronic side more than anything else, other than our thermostats, of course, is probably our zone valves. There's a reason for that. We've got several patents on this valve that we have come up with that make it very robust, make it very, very long-lasting, and make it very easy to install and work with. So what we do is we've got 2 different series of zone valves, and I'll talk about both of them. But with the first series is our 1000 series zone valve, which consists of mainly 2 components. You have a valve body. It's probably better on this side. You've got a valve body here, as well as a motorized power head on the top. We sell them packaged as one unit. We do sell replacement power heads, which is all the basically aluminum looking piece on the top that can be dry fitted onto a valve body without any issues. Because this is a mechanical piece of equipment, just like a pump. Mechanical pieces of equipment, after so many cycles of operation, everything will eventually fail. I wish to say ours never would, but ours will fail eventually. So depending on the use, depending on the water quality, there's a lot of different factors on how long a valve will last. So if you've got a lot of junk in the system, it wasn't put in, you don't have any boiler inhibitors, chemicals, anything inside of it. If you got a lot of junk, it's a lot more strain on the motor. If you didn't have, when you put in heating systems, it needs to be closed loop, meaning there's no oxygen. I have seen systems where oxygenated tubing was used, so instead of HEPEX, it was AquaPEX. You're constantly reintroducing oxygen molecules. It will corrode the inside of these valves, and you will get maybe 5 years out of them instead of the anticipated 15 to 20. And I think we have another question.
Yeah, Pete in Texas asked, what is the warranty on Honeywell Homes Hydronics products?
What is the warranty on the Honeywell Homes Hydronic products? So, good question, and I'm going to start by saying all of our warranties do not start from the date of manufacture. All of our warranties start from the date of installation. So that's one thing to keep in mind, because if you buy something and you keep it on your truck for 1.5 years and then you install it and then it fails down the road, then it's from when you installed it. The majority of our products is 1 year from date of installation. Our circulators, our pumps, we actually run a 5-year warranty on our pumps. But if you need a general rule of thumb, 1 year on pretty much everything.
All right. A couple more quick questions.
Yep.
Vinny from New York asked, how do you get the zone valve from banging when closing?
Good question. Can we counter that with a second question? Is it our zone valve or somebody else's?
It must be someone else's.
It must be someone else's. Now, actually, I do have a serious question on that one, and I'll talk on some of it. So he's referring to water hammer, and I will touch on that. I'll tell you what. Let's touch on that, and then we'll circle back to it, because I have a slide here in a minute where I'm going to be talking on that.
All right. 2 more questions. They're flowing in now. Ricardo asked, is there, let's see, is the low voltage power to the zone valve constantly energized?
No. So what you're doing is these are spring return valves. So if it does not have power, that valve will be closed. Or actually, I think I know what he may be asking. When you go to activate our valve, it will need 24 volts consistently. So with this series of zone valve that we have in front of us, this is by far the most common in heating systems, you have to give it 24 volts and maintain 24 volts to keep it open. When you kill the power to it, what it's going to do is basically bring it back closed, because that spring is going to draw it back. We do make a series of valves, which I unfortunately do not have in this presentation, that you can open it and close it without having to keep it energized. So it's a 3-wire style, whereas this one only needs 2 wires to open up. That series of valve needs 3, because you have to give it 24 volts to open it, and then you have to give it 24 volts to close it. So I don't have that in this presentation, but we do have a different series of valve that could handle one that doesn't need constant power.
2 more questions.
Sure.
Leon asks, do you offer a 3-way mixing valve in 1/2 inch for hot-cold water coils?
3-way mixing and diverting are a little bit different. We do have that product offering. It's in that same series of valve I was talking about, where it's power open, power closed. Okay. Because in a mixing valve, you have to give it to a certain level of operation. So you typically have some kind of a control that's sensing it and driving it somewhere. We do have some products that can handle that.
All right. Constantino asked, I thought that the Series 1000 came normally open or normally closed, depending on how you order. You said they're normally closed.
Good point, and I do stand corrected. So on our valves, I lean on normally closed because that's the majority of what we see. However, there are areas and applications where you want to run normally open. Actually, I covered Canada for a little bit, and up in Canada, the most common zone valve is actually normally open, because they run such cold temperatures. If a valve fails, they want it to fail open so that the systems can still drive heat through that area. In the US, we typically see normally closed, but there's applications for both.
All right.
Good questions, though. Yes, because I did say normally closed, and I tell you what. Let me jump to a slide. So here's our different configurations. So we've got normally open, normally closed, and we also have diverting valves. Again, diverting valves and mixing valves are two different valves. They're both three ways, but in a diverting valve, think of it as you're literally just diverting water from one direction to the other. In a mixing valve, you're going to be proportionally adjusting the flow of water between one side to the other depending on the outlet temperature. So we have both, but in this series of valve, these are only going to be diverting because they're 24-volt open, 24-volt close. Or 24-volt close, 24-volt open, depending on to Constantine's point, yes, depending on the configuration ordered. And we've got these 1/2 inch through 1 inch. How do I have my slides arranged here? So I'm going to talk about coefficients of velocity. I get asked a decent amount for 1 1/4 and larger zone valves. Most of the time, they're not needed. And I'll talk about that based on close-off pressures and flow rates in just a second. Question from the audience, yes.
James, love it. He said, I have to say this guy is good, so I think they appreciate your candor there. That was awesome.
Okay,
So.
thank you. So my water hammer question that we had, I'm gonna touch on that briefly. As I had mentioned on our zone valve series, now when we were talking earlier how we have valves that 3 wires, you can open it and close it, that's a different style of device. That's more of a globe valve actuated than it is. It's more of like a piston style than this series. But in this series, we have this ball inside of here, and I wish I had a cross section to show you. But this ball basically sits on like a little spindle. So that spindle is what opens and closes. That ball will actually twist on side of there. So what's happening is every time it closes on side of that, it's closing in a different spot. So the longevity of the guts of this thing are absolutely phenomenal. What happens on a paddle series valve, which I'm not going to pick on any manufacturers, but there's several manufacturers that use a paddle series valve. What happens with the paddle is it's a lot like a toilet flapper. So when that paddle shuts, what happens is it's shutting all the water off very hard, very fast. So it not only creates the potential for water hammer, but it also provides accelerated wear because it's always closing in the exact same spot every time. If they did not treat, if the boiler's water wasn't treated before it was installed, it'll actually even accelerate it more. Ours will get eaten up eventually if the boiler water is not treated. But what happens on ours is it's sealing on a cup with ours because it's a ball basically sealing on a cup. So not a whole lot of potential for water hammer, but our 1000 series valves can still have some water hammer. So if you're getting it, and that's why I was asking if it was our valve or not, if you're getting it on our valve, you may want to take a look at the system. There may be something else that's causing that. But, I lost my clicker. With that being said, we do have another series of valves. So we have a 5000 series. We got real creative with the numbering system here. So our 1000 is our basic one. Our 5000 has a slightly different valve body, but really the beauty of the 5000 is the power head. What we've done is we've put an extra spring in there, so it's a much more controlled, slower closing operation. It's also a more consistent because those springs are much heavier duty. So what happens is if he does have a job site where, let's say it's one of our valve bodies, you can go in and put in a 5000 series power head. So I'm going to try to talk through this one a little slow. So on the 1000 series valve, it's got the body and the power head on there. The 5000 is a slightly different body, but we have engineered it to retrofit onto the 1000 series bodies. So it's as easy as, I don't have a screwdriver with me, but if you were to take this screw off, this comes off. There's 2 screws inside of here. Let's see if I can figure out which one they're on. They're caddy corners, so there's going to be 2 screws that are securing the power head to the valve body. You remove those 2 screws, you take the new 5000 series power head, and you can tell the difference because the 5000 has a rounded top. It literally plugs right back into the same spot, and 2 screws secure it back to the valve body. Now, one thing I will say, our zone valves, both series, are engineered to only operate when physically and securely attached together. We get calls every now and then from people that say that our zone valve heads are stripped out. If you try to operate, we have a manual opener on all of our zone valves, and I'll kind of show you how it works. You'll see it slowly close here. What happens is these are normally closed valves, so you've got a spring that always keeps it in the closed position. You can manually open it, literally by just pulling it and pushing it to the side. It actually has a catch, so I can leave it open. The reason we do that is when you commission a job site, you got to purge, you want to leave all your valves open. If you try to operate this, when it's not screwed down securely to the valve body, the gear assembly does not line up properly. They're engineered so the gear assembly and the body have to be bolted together in order to line up. So if you just took a handful of power heads not mounted and tried to operate these things, they would act like they're stripped out. The reason is the gear assembly floats inside of there because it's designed to bolt onto here. If it's floating inside of there and you're trying to operate that lever, it'll feel like it's stripped out. It's not a big deal. As long as you haven't been playing with it, you can put it back on and it'll go right back to normal operation. But I mean, I can operate this thing over and over and over on top of the valve body. It'll work flawlessly every time. Eventually these can wear out. Yeah, question.
Ricardo asked, are there pneumatically controlled valves?
Honeywell Commercial, or Honeywell International, does sell pneumatically controlled valves. We are no longer affiliated with that company, so our Residio Honeywell Home, just try not to make it too confusing for anybody, but Honeywell Home does not offer pneumatic valves. If you need pneumatic valves, Honeywell International does offer pneumatic valves. Keep losing my clicker here. So the 5000 series, our Mosbach Germany, and I don't mean to pick on another manufacturer. I'm hoping you can't, I did list the name. This is basically oscillating curves based on what happens. This was tested in our Mosbach Germany factory, which is where I had mentioned most of our valves are made. They tested a paddle style valve as well as our 5000 soft close. So to your customer that said that they've got one that's delivering some water hammer, if it is our valve body, I would suggest throwing in the 5000 series power head. I'm very confident that that will fix the problem. If it's not our valve, you could probably even start with our 1000 series. It would probably do the job, but 5000 is very effective at controlling water hammer. Let's see, CV rating. We're going to get into a little bit more math. I apologize in advance. So we make sizes 1/2 inch through 1 inch. I get people on residential systems that go to 1 1/4 inch. And the reason they go to 1 1/4 inch is because they need more flow. Every valve, whether it be a zone valve or whatever, is going to have a CV rating on it. That CV is essentially telling you what the pressure loss through the valve is. The smaller the number, the more resistance you're going to have. So as an example, we've got 1/2, 3/4, and 1 inch valves. All three of these have the same CV rating. So you're going to have the same resistance, feet of head pressure loss, through these valves regardless of what pipe size you're using. The reason we make varying CV rates is the lower the CV rate, the higher the pressure, the higher the close-off pressure. So if you were to use what a lot of people refer to as a full port zone valve, it is true you would have slightly less pressure loss through that valve, but your close-off pressure dies off. So when we look at this in a 3/4 zone valve, we have a, and my number's not up here, but we have a 3.5 CV rating, which is one of the most common. I think that's actually the one here I have in my hand. It looks like it's got a little bit of resistance on there, and that's true. But we also make a zone valve in a 3/4 inch that has a 6 CV rating. So the 6 CV rating looks almost like it's a full port. It's technically not, but it's much more open than the passageway through that one. When you're looking at pipe sizing and zone valve sizing, this doesn't necessarily make or break it based on pipe size. So if you've got an 1 1/4 inch because you need to deliver 10 gallons a minute, you see down there where I have a couple of valves that are listed between 8 and 10 CV. I've got some 1 inch valves with a CV rating of 8. What CV means in a nutshell is if I'm driving, let's say I have a CV rating of 8. If I'm driving 8 gallons a minute through that valve, I will have 1 PSI of pressure loss. 1 PSI of pressure loss, remember that formula I gave you earlier, is equal to 2.31 feet of head. In a hydronic system, I mean, you saw the pump sizing. Adding 2.3 feet of head is very rarely going to do anything with the sizing of the circulators in the system. So if you're doing an 1 1/4 system, I see it a lot of times with an 1 1/4 line that's driving, let's say 8, 9 gallons a minute, it's maybe going to add 3 feet of head. So you can easily take an 1 1/4 line in most instances and reduce it down to 1 inch for the valve. When you get into an 1 1/4 valve, we sell some in some different series, your price is going to quadruple immediately. So plus it becomes a little bit more complex on the wiring and control. It's a little different valve. And we have a question.
Yeah, it was actually a statement. Constantino said basically he had a valve installed backward and that caused the hammer sound. Is that can you comment to that?
Yeah, because it's not opening and closing right. Best case, I wouldn't throw our 5,000 on it. I would cut it out and put it in the right flow direction.
Okay, so don't install
I'm honestly
backwards.
surprised it was working properly, to be honest. But yeah, if it's installed backwards, they're all stamped with the flow direction on them. So best case would be to cut it out and put in, orient it correctly.
All right, got another question from Extreme Refrigeration. Industry is going towards Wi-Fi. I think he's asking, does Honeywell Homes have any valves that are Wi-Fi enabled?
The valves, no, but the thermostats that control the valves, yes. Okay. So when we're looking at, and I'll touch on that briefly, what we're looking at with the valves is all the logic for the Wi-Fi part is controlled essentially in our thermostats. So we don't use, I'll touch on that with the hydronic panels, but for now, let's just say not on the valves themselves because all the feedback's going to all be from the thermostat.
Okay.
And then just real quick on your CV, if you guys want to write this formula down for those of you that are there, I believe you guys are making this available for PDFs as well. That formula is handy for that one that I've highlighted. You can find out what your pressure loss is. So all you got to do is take your flow rate, divide it by whatever the CV rating is, multiply it by itself. That'll give you the PSI loss through there. And then to get feet of head, you just multiply by 2.31. So if you ever need to figure out, am I going to be running up against too much pressure through a valve, just take your flow rate, divide it by CV rating, and multiply it by itself. And then I'm going to flow through this pretty quick. I had put a zone valve selection guide on here, but I'm running a little tight on time. I will make this available to Jackson Systems, so we make many different types of zone valves. With that being said, probably 8 of them make up the lion's share of our business. But we have a zone valve selection guide here. So this kind of breaks you through what all the numbers in that zone valve mean. So if you're looking at a V8043E1012, what does that valve mean? It means it's low voltage, it means it's two-way, it means it's got 4 wires on it, and it's 1000 series, and then 3/4 inch. So it all breaks it down. I got 2 different slides because there's a lot of them there. I'm going to pause briefly and then keep rolling. That concludes the mechanical segment I was going to talk about. So before I move on to any of the control aspect, when we start talking about smart home, Wi-Fi, relays, etc., does anybody have any questions at this point? And I'll pause just a moment.
I think you're good.
Okay. So getting into controls. Before I start with any of the product piece of this, what I want to do is just kind of cover the basics of a circuit, because you kind of got to understand the basics of how a circuit works before you get into understanding our controls and how everything links together. So, and this may be a little bit elementary for some of the people that are on, and so I'm going to go through this relatively quick. But in a control circuit, there's always 3 components. You've always got a power supply, you've got a switch, you've got a load. So if I went to a high school that was a little, or probably not high school, elementary school that was a little bit more high tech, this is a good example of about as rudimentary a control circuit as you can get. So we've got a power supply as a battery, we've got a big lever there as a switch, and a light bulb as your load. So as your power goes out, goes through a switch. When you create the switch closure, you're going to power up the light bulb, and power makes it back to the same power supply. in our world, I'm going to show you kind of how that relates. So when we're looking at power supplies, on the 24-volt side, it's typically a transformer. On the 120-volt side, that is usually power coming from your circuit breaker. And that could be 208 volt, etc. But this is kind of what we're looking at on our side for the power supplies. Switches, a couple examples of switches. Probably the most common, based on the conversation we're having today, is thermostats. Thermostat you put up on the wall is nothing more than a very glorified switch. You're sending power up to it when there's a call for heat. In other words, when the temperature drops, you're going to send that power back out through it. It's no different than a glorified light switch. We also have Aqua stats, light switches literally, and then spa timers. And then when we look at switches, there's a couple of different things. I was going to touch briefly on some of the relays. When you're looking at switches, you can have single pole, single throw, meaning, and I think Carol Fay writes a book, forget the name of it, Quick and Easy Electricity, I believe, but I'll give her a quick little plug because I read her books when I was learning hydronic controls. But Carol Fay relays this a little bit to fishing poles. So when you're looking at single pole, single throw, you're taking a fishing pole and you're throwing that power one way. So think of your line as essentially your electricity. Single pole double throw means you're taking a fishing pole, a single fishing pole, and you're throwing it one direction or you're throwing it a different direction because it's going two throws. So you're giving it two tosses, two casts. Then we just keep getting more complex. So now we got double pole, single throw. I got two fishing poles and they're going the same direction. Double pole, double throw, I got two fishing poles and they're either going here or they're going here. But easiest way to kind of keep that in mind when we get into some of the relay controls is how this works. And examples of load to finish up our basic simplistic control circuit. We've got on the 24-volt side, we have zone valves. And on the 120-volt side, we've got circulators. There can be more examples of that, but that's pretty simplistic and basic right there as far as what we use. When we put it all together, remember in that circuit that I have up in the top, battery to switch to light bulb back, that's basically what we have in a low voltage hydronic heating circuit. So we've got the transformer, so taking our 120 volts, converting it to 24, we're throwing it up to the thermostat. Once that thermostat gets a call for heat, it basically throws the power out to the zone valve. The zone valve then gets the power and you have to complete the circuit and it goes back. As you guys are learning, if you're not real proficient in electrical circuits, one thing I will advise you on, because it'll help you a lot as you get into more advanced circuitry, always start from the power supply, go out and come back. Don't ever work backwards because as you get into more complex controls, it will start to get very confusing. So you always start from the power supply and move out and come back. So in our system, we sell, we at Resideo and Honeywell Home, we sell a lot of transformers. So if you wanted to hook up a simple system with a transformer, this is essentially how you would do it. You're going to come from the transformer, and I'll give you a hint on some of the wiring if you haven't seen some of this. You have R and C on a transformer. When you're wiring up a thermostat, you typically take the R from the transformer to the R on the thermostat. It's basically the load side of that transformer. And we talked about it being a switch. So if you look at a thermostat subbase, you'll see a whole bunch of different letters and characteristics. So what we're doing is we're taking 24 volts into R, and then we're going to throw it to different things depending on what the thermostat's doing. So if it's calling for heat, because we're talking about hydronic heating, it's going to basically throw a switch between R and W. So then what we're going to do in this example I've got behind me, we're going to take W down to that zone valve, the motor, be careful not to hook it to the end switch. The other side of that motor goes back to C on the transformer. So we've now completed our circuit. So what happens is we basically take power up to here. It sits on the thermostat waiting for something to happen. That temperature drops, clicks the relay. It's now sending 24 volts out across W down to the motor. And then you have to complete the circuit. So the other side of the motor has to go back to the zone valve. I'm sorry, the other side of the zone valve has to go back to the transformer. And you're going to hook it on C. So now you've used both sides of the transformer. That's our simple two-wire zone valve system. The problem with this example I'm showing you is that there's really no one zone valve system that exists today. So what we do is we hook up 2 thermostats. So we've got 2 thermostats and 2 zone valves. So what we're doing is we're taking R off the transformer. We're going up to R on both thermostats. So we're putting 24 volts on both thermostats. The W comes off of the corresponding thermostat to the corresponding zone valve. So let's say zone 1 is the thermostat on the left and the zone valve on the left. We're going to take W from that down to one side of that motor. That motor has to go back to the transformer. We're going to take the W off the second thermostat and go to the zone 2 motor on the zone valve. Then we're going to take that motor back to the transformer. So think of it as you're loading up both thermostats with power. Where do you want that power to go? And the power has to make it back on both of them. So we sell a lot of thermostats, got lots of different capacities, sell lots of zone valves. There is nothing wrong with doing it this way. However, I've been on a lot of job sites, and in my previous life, I got called out typically when nobody could figure out what was going on with the wiring and why the boiler wasn't working and why the valves weren't opening. I've been on a lot of jobs, and I've seen everything from a wire nest like we see on the left to what looks like a very professional install on the top right, where everybody kind of twisted all the wires together but then jammed them inside a junction box. That is incredibly difficult. While it will work if it was wired properly, that is a nightmare to troubleshoot. I have walked in on a lot and said, I'm not even getting my voltmeter out. Let's just cut it all and start over. So it's very time consuming. It can look good. It works just fine, but the problem becomes, what do you do down the road when you need to go back to the job site if there's any kind of an issue, if you have to access it to service it? It becomes a giant pain. So what we've done is we've finally created, because we've had high-level controls for a while, we created a very simple relay control. So it could be with zone valves or pumps. But we've got these hydronic panels now. You've probably seen some stuff very similar to these in the past, but this is nothing more than think of it as the landing point between the zone valves or pumps and the thermostats. So it's going to take the call for heat from the thermostat, tell either the pump or zone valve to turn on, depending on how you're doing it, zone valving or pumping. And then it's also going to tell the boiler to come on. So if we look at a cross-section here, here's essentially the guts. Now I'm showing the zone valve relay. So for those of you that zone pump, I apologize, I don't have a cross-section on it in this presentation. But it's essentially the same principles here. So what we've got up across the very top, and I actually have one, got one here with me. So this is what you hook everything to. Now the beauty of this is when I get the cover on, you saw the pictures I was just showing you where you saw wires going everywhere. What happens here is you've got LED diagnostic lights. So it's going to show you what zone is calling for heat, what thermostat is calling for heat up across the top. Down at the bottom we have the zone valve that's calling for heat, or if the pump should be turned on. We have the all-inclusive, does the panel have power? So we have a power light on here. And then you've got a couple other LEDs on here. So you've got boiler, we have an extra in switch, and then priority. So everything's color-coded, and it gives you a visual representation. You can walk up to a job site immediately and identify, at least by this, what zone is calling for heat, what zone valves should be open, what pump should be running, should the boiler be turning on, etc. So there's no getting out your voltmeter, there's no tracking stuff down. You can immediately figure out what's going on. And I think we have a question from the audience.
We do, from Ricardo again. Suppose the T-stat has its own battery. Do we still need the common from the transformer?
Good question. No, you don't. So this will work. And I think where he's getting at is if you look at the top of our control, you'll see an R, W, and C. So what we have done is this is just looking for a contact closure across R and W. So if you wanted to play with this, you could actually take R, just a jumper between R and W, and you'll see that light pop on. The C, my own, I think I just covered up my microphone, my own personal comment on that is I would go ahead and hook them up. The reason I'm saying that is a couple of things. One, batteries go out. It's nice to have them as backups, but I like having everything hardwired. And two, I always recommend people run a minimum of 4-strand thermostat wire. And the reason I say that is I have helped people wire stuff in the field, and I have seen brand new thermostat wire that gets run behind a house. Everything gets sheetrocked, painted, etc. Then it's time to hook up the thermostat, and guess what? One of the wires is busted. We have a solution for that. Don't worry, but it's very expensive. So I always recommend running at least 4. You only need 2 if it's a simplistic hydronic system, R and W. I always recommend hooking up the C, which is going to be your constant power to the thermostat. The other reason I suggest that is there's more and more people migrating to smart home products. If you've only run 2-strand wire in the wall, it dramatically limits your thermostat availability and offering. If you run 3, all of our Wi-Fi thermostats work perfectly well off of 3 wires. So that C basically just powers the Wi-Fi radio inside of it. Wi-Fi radios draw a lot of power, so if you don't have it, there are some other products you can find on the internet that will only do 2, but your homeowner will not be happy. You end up changing those batteries every 3 to 6 months.
All right.
So
one more quick question
Yeah.
from Constantino, and I think you're probably going to be answering this in a minute, but he asked, how many zones can you control?
good question. So I haven't even used my favorite hydronic answer to questions yet. It depends. So what you're looking at with this is how many zones can you operate with this. So in this example, I am holding in my hands a 5-zone control. Depending on the boiler you're using, you can ultimately indefinitely expand these things. So it depends on the boiler you're using, and it depends on the relays that you need to operate. Most of the modulating and condensing boilers that exist today, and I've got a couple of diagrams here. So in this example, down in the bottom, you'll see I've got a boiler with an indirect water heater, and this is very typical of a cast iron boiler or a copper fin boiler. So what you're going to do is you're going to wire the pumps into this board. So when there's a call for heat, you need to turn a pump on, you need to turn a pump off, depending on what's calling. Is it the indirect water heater, or is it a system? We can do domestic priority as well, but what you're going to do is if you need to wire the pump terminals in here, you're going to lose a zone on every panel, because what you're going to do is you're going to sacrifice one. And I've got some wiring examples here in a minute that show that, but you're essentially sacrificing one. So if you had 10 zones, you would need to buy zone panels with the capacity of at least 11. I said 10 zones, so 11 zones, because you're going to lose one zone as a jumper. But yes, you can ultimately expand these indefinitely. The other thing that we've seen is there's more and more people using modulating and condensing boilers. With ModCom boilers, most of them have the pumps wired directly into the boiler itself. So you're going to have your indirect wired into the boiler, you're going to have your space heating and boiler pump all wired into the boiler. With that being the case, literally all this is a zone valve relay or a pump relay. So you can just give calls for heat indefinitely. So you can put 2 boards side by side, so if it's a 10-zone system, you can put 2 5s side by side and take the boiler in switch off of each one right back to the boiler, because you're not using the high voltage relays.
Another quick question, no shielded cable needed.
Nope.
Just regular thermostat wire.
Regular thermostat wire is fine. Shielded cable is typically used when you have resistors. So sensors are kind of what drive that. With this, all we're doing is opening and closing relays, so it just needs kind of an on-off call. So yeah, shielded wire doesn't work. It works fine, it's not needed. Any other questions come up? A couple of things that we've done to this board that kind of give it some value to you. One, the way that we install this on the wall. You don't have to basically hold it against the wall, try and level it while screwing it at the same time. We've provided a keyhole mount here, very similar to hanging a picture. So you can zip a screw into a stud, hang it like a picture. It somewhat self-balances, and then once you get it secured to the wall, we've got a couple of screws that you can basically just level it and screw it in there. So much easier to mount against the wall. We have also got a grounding wire on the zone valve instead of a grounding screw. So you've got a little bit more flexibility as far as running your wires through there, because this can get congested. We have one of the biggest selling features on this. We have the ability of running power stealing thermostats. So if you have a 2-wire power stealing thermostat, it will operate off of here. There's no need to come back and add resistors down the road if somebody changes it or add them from the initial install. We also have field replaceable transformers. I have been guilty, I'll go ahead and own this one, of wiring things incorrectly and hearing the good old pop and then smelling the smoke that I let out of the transformer. If you do that with this, we have additional relays packaged in, or I'm sorry, additional fuses packaged in the casing. And these transformers, we did them with wires so that in case you do blow a transformer, if you've got a universal 40 VA transformer on the truck, you can bring it out, screw it right next to it, and wire it right back in where the one that doesn't have any smoke left in it is. So there's no need to replace the entire board because you blew a transformer. So with that being said, if you did something catastrophically wrong and you fried the circuit board, that is possible, but 9 times out of 10 it just ends up popping either a fuse or a transformer. So you've got the ability of kind of getting this thing back up and running in the field. So we talked about zone valves and zone pumps. So this example that I'm showing you up here is typical wiring for a zone valve system. This wiring here, basically the exact same configuration, but instead of valves, now we're using zone pumps. So you lose the system pump and you add the zone pumps. You see the wiring is still incredibly simplistic. The top of that panel still gets wired exactly the same. The only difference is instead of valves, now we're using pumps at the bottom. So 14 or 12 gauge wire hooked into the circulators. So I think it was Constantine that asked the question about expanding the boards. Here's one example of that. So there's different configurations. We actually have a wiring guide available on the internet now that goes through a bunch of different circumstances, and I'll show a couple of those here in just a minute. But what this does is you can basically just take the boiler TT off of, call it the slave board, drop it into the master on any one of the zones, and what that's going to do is sense a call for heat, and that's the master board basically sees that secondary one as a giant thermostat. So if any one of those thermostat calls for heat, that's what it sees. In order to make that work, because we're not hooking up a zone valve, I never really touched on what an in switch was. So I'm going to back up just briefly. So when we talked about zone valves, I said there were 4 wires are the most common ones that we see. 2 wires do the motor. The other 2, which are I always get this backwards, the 2 red ones are the in switch. The in switch is nothing more than a proving switch. So what happens is when this valve opens, it's going to close continuity across these 2 red wires here. The reason we do that is we don't want to turn a pump on or a boiler on if the valve is not indeed opened. It takes a couple seconds for these valves to open and close. So it basically builds in a delay and waits to make that contact closure. One fact about that is only done electronically. If you manually open this valve, it does nothing to the in switch. So it has to be powered with 24 volts to get the in switch to close. So our board doesn't tell the boiler to come on until it sees a contact closure across the in switch. So we can trick the board in this example by putting a jumper between 3 and 4, which is our in switch closure. So basically when it sees a contact closure across the thermostat, it sees that in switch is closed and immediately tells the boiler to fire. So you can also do that same trick if you have 2 wire zone valves with no in switches. Another series of products that we have had for a while, and I'm going to touch on 2 big pieces with this, is our Aqua controls. These are really neat controls because what this does is it adds, this is really just a simplistic relay, simplifies the wiring, lets you know what's going on. You've got LED diagnostic lights. This adds some actual logic and brains into the system. So what this does is it has a self-resetting transformer, gives you the ability to do pump and valve exercising, gives you zone synchronization, which I will touch on because that's a pretty big deal, as well as it's got some additional terminals where you can do some more stuff with it, depending on what you're trying to do in the system. But one thing I want to touch on is what zone synchronization is. So I've got a couple of slides up here. In a typical hydronic heating system, because we love the zone hydronic heating systems, I've been in houses that are 2,000 square feet that have like 15 zones in them. That's a little excessive. So what happens is, let's say we've got, even today's boilers, our modulating and condensing boilers. If we put in a 100,000 BTU boiler, if that boiler basically modulates, say it's got a 5-to-1 turn down ratio, minimum firing rate is 20,000 BTUs. Sounds very, very small. The problem is if you put 15 zones in a 2,000 square foot house, some of those zones on the worst case scenario, design day conditions, only need 800 BTUs, 900 BTUs, and it's very rare that all thermostats are calling for heat at the same time. So what happens is, in this example, I've got a 3-zone system. And it's showing kind of what's operating in the system, because the boiler in this product, as well as just wiring up with the transformer, we just tell the boiler and the pump to run anytime any thermostat in the house or building or whatever calls for heat. So what happens in this example, I give the analogy for this actually. Let's say there's 3 of us going out to a restaurant, we're sitting down and getting some water. And we've got a waiter that's helping us. So he comes out to us, and let's say I'm really thirsty. So we've been sitting down on the table for a couple of minutes, and let's say you have drank a little bit of your water, I've completely finished mine, and you've got half of yours left. So the waiter, let's say hypothetically he came in and he filled mine up and then left. Well, he's going to be right back because you're almost done with yours. So he leaves, he's gone for a minute or 2, and then he comes back, he fills yours up, and then he leaves. Well, now Brian's come through, and by now he's finished his, so 2 or 3 more minutes come by, he comes back and fills it up again. So what happens is that's basically what happens in a hydronic heating system when you zone it. So one zone calls, it shuts off, then another one calls, it shuts off. So that boiler is just on, off, and it can't meet the minimum firing rate, so it's just cycling. So what we do in this example is same scenario, but let's give it that same example of 3 of us sitting down, we're getting water. So I've finished mine, comes back over, so he tops my glass off. While he's at the table, he fills yours up and yours up. And then he leaves. Well, now we're only waiting on the zone of greatest demand, or the thirstiest person, to come through and drink down to where we're going to need it again. So that's basically what this does, is it puts a delay on the call for heat to the boiler based on what's happening in the system. So we've got 2 options and 2 ways of doing this. The first, we actually have communicating thermostats available that will sense the usage. So it's actually seeing the temperature go up and down and adjusting the firing rate according to that. So if it sees one getting ready to meet, it basically delays it to see if it can get any others. Or when it kicks on, it sees if any other thermostats are close to being close to a call for heat. That's great, but there's a lot of people that don't like communicating thermostats. There's only 2 that we offer. Maybe they want to use standard, maybe they want to use Wi-Fi, maybe they want to use a high-definition color display. So we went through and retrofitted the device and gave it the ability to operate with standard thermostats. You lose some of the efficiency out of it, but what it does is you're able to put the entire system in, you're essentially setting it for cycles per hour. So it will put a delay on the last call for heat. So let's say you got a call for heat on all your thermostats, and then it shuts off, and you get another one that calls 2 minutes later. It's going to delay the boiler firing for, could be 5 to 10 minutes, depends on how it's set up. So what it's going to do from there is, in a radiant heating system, if you shut the water off for, say, 5 to 10 minutes, it's not going to do anything. There's going to be no perception made to the end user. The one exception to that is hydronic fan coils, because you're blowing air again. But any kind of hot water radiant, if you shut it off for a short period of time, they're not going to feel it. But it will basically produce less cycling on the boiler. It's not dramatic on the energy efficiency savings. It's roughly 5%. But what it does is it prohibits some of the boiler cycling, so incredibly less wear and tear on the equipment. The other thing that's neat with this, and I wish I had one that was live fire, you can literally jumper between R and C. So anybody that's done that on a transformer, what happens? It goes pop. This one, it's auto resetting. I have no idea how the engineers did this, but you can put a jumper between R and C. You can watch sparks fly, and it'll just keep going. So that's fun to show. I should have brought one of those and plugged it in. And then these are also expandable. So you can hook up to 16 of these together, and they literally hook side by side. So there's even some grommets on the side that when you put them next to each other, you can flip them upside down, and you create a wire path between the boards, completely encompassed behind. That one doesn't have the outer covers on it, but completely encompassed behind the covers. Boiler staging. I saved all the hard technical stuff to the end. I probably should have led with that. So Boiler staging controls. So we offer a product called got real creative with the name, the T775. Don't know where the number came from, but that's what we've got. So our T775, we make it in a bunch of different configurations. In the radiant world, we've got two of them that I see probably more than anything else. So the first one is boiler staging controls. So whether it be a super high-end residential system that has two boilers, or light commercial, heavy commercial, whatever you're looking at, we have the ability with this control of handling boiler staging. With that, we can do lead lag, we can do equal runtime. There's different types of configurations. It's got warm weather shutdown, outdoor reset, and it's expandable. So if you've got, I have used these on jobs where we've got up to like 5 or 6 boilers. You can basically expand it and keep them daisy chained all the way through. So if you've got 2 copper fin, 2 cast iron, we see that a lot in commercial jobs because, well, 2 reasons. 1, you want redundancy, and 2, you need the lower firing rate to I'm getting to where I can't talk, to eliminate some of the short cycling as well. So you can get to a lower firing rate as well. We also make a version of this. I don't have a slide on it. We make a version of this that's an outdoor reset control that can handle a 3-way mixing valve as well. So if you've got a modulating, I think there's a question earlier about mixing controls and mixing valves. If you have a mixing valve that takes a modulating input, we have a version of this control. It's still a T775, but the ending's a little different. You can give it a modulating input based on outdoor reset and a temperature sensor on the outlet of the pipe. So we make quite a few of these. They're also used in the HVAC world, but it's basically just a digital input-output control. Okay, fun stuff, thermostats. We make lots of thermostats. I mean, I think there was a study run a long time ago where I don't know if it was our marketing people or somebody else made calls to people and asked them what brand of furnace they had. And the most common answer was Honeywell. We've never made a furnace, but people affiliate us with the thermostats on the walls. So if you pulled out our line card today, and we actually just with the creation of the T-Series consolidated our line quite a bit, we still have probably 50, 60 different thermostat model numbers. They're all a little bit different. They all achieve a slightly different purpose and look different, et cetera. But we've got a list of probably 12 to 13 of probably the most common thermostats used in radiant heating systems. I've also got a reference guide for you all on how to identify what our model numbers mean. There is a method to our madness. So just kind of breaking it down real briefly, TH means it's a thermostat. YTH means it's a thermostat packaged with something else. The number is the designation of the thermostat line. We have actually, I think I don't have it on here, but we have an X now, just like on iPhone, so we have a version 10 with our new T10. And then we have the system stages for heat, which I tried to do in red there. So how many stages of heat can it handle? The next number is how many stages of cooling can it handle? The next set of letters designates kind of what it is. Is it a universal, bi-fuel? Is it Wi-Fi? What is it? And then from there, we have 4 more numbers that could mean anything that you want to dream up. It's whatever our engineers decide that they want to assign to the valve or to the thermostat to give it a little bit more of the particulars. One of the things that we've done, and since we're talking about hydronic heating, the most prevalent thermostat that I've seen in the hydronic heating world has been our Pro 1000. Very simple, heat-only, vertical, digital thermostat. We sell lots of that thermostat. With the invention of the T-Series, I urge you guys to start looking at the T1. It's a much more modern-looking version of that thermostat, and it still does the same thing. It's very simplistic, non-programmable, and you can set it for heat only or cool only. The neat thing about that is it uses I'm going to go back to this, we created what we call a universal wall plate. I kind of have it mounted here to a goof box a little bit, but what you're looking at is this one little wall plate fits every single series of thermostats. So when we're looking at radiant heating, the nice thing about this is you can start with a heat only, and it gives you an upgrade path into Wi-Fi without having to do any change to the wiring. So if you wire one up, you can offer them a Wi-Fi option as an upgrade. That's a very, very simple change out in the field. When you're looking at our T-Series thermostats, kind of going least expensive to most expensive is our T1 all the way up to our T10, which is a high-definition digital display. Radiant heating, I got the question earlier today, you know, how much does radiant heating cost to install? So those of you all that have been doing it, it's more expensive than forced air is pretty much every way you do it. So with that being said, what drives the radiant heating market? It's the high end, the people that want to spend money for luxury, comfort, etc. Or they've got an existing system and they just need to get it working again. But with that being said, a lot of people are willing to spend the money towards nicer thermostats. I mean, we've seen a very big transition into smart home. You can very easily make a radiant system connected. I've got a couple of different ways. So I think I had the question just a minute ago about how many wires can you run the C wire to the thermostat? Can it run off batteries? You can. The reason I say always run 4 is I put together a little cheat sheet here because we do have solutions for thermostats that don't have wires in the wall. It happens if somebody ran 2-strand wire and, I mean, one of the wire breaks, it could be a rat chewing on it. I mean, I've heard all different types of things. But if you don't have wires in the wall, we do have some options for completely wireless solutions. What you do is you have to use our RedLink products, which is a proprietary wireless communication, and you put a thermostat out in the house or the room or whatever, and you put the equipment interface module back at the boiler. The equipment interface module is really nothing more than a glorified back of the thermostat. So it's wirelessly talking to the back of the thermostat. That back of the thermostat is what would get wired into our hydronic panel. So instead of running thermostat wire up to the thermostat, you're going to run thermostat wire to the equipment interface module. And that equipment interface module is going to wirelessly talk to the thermostat. So that's how we do wireless thermostats. I've got 2 options, well, technically 3. I've got a Focus Pro series and a Vision Pro series. They're not the cheapest, and if they want heat only, that's a very expensive way of doing it, but you can do wireless without having to run wires in the wall. If they want to get on the internet, we can do it with 2 wires with these 2. So the first is our Prestige. So high definition color display, that's actually the one that I just put in my house. It needs 2 wires. And the Smart Round Wi-Fi also needs 2 wires to run. So that Smart Round Wi-Fi, just something to point out on that one, it's 2-wire installation. You can run it on 3. I would strongly urge you to run it on 3. But if you want to run it on 2, you can do it. Something you need to keep in mind, when you first turn that valve or that thermostat on, you have to give it a constant call for 3 minutes minimum. The reason is there's a supercapacitor inside of there, and it has to learn the energy draw of the valve and everything else to operate properly. If you don't give it a 3-minute call, it's possible to have that zone valve open halfway and then shut off. So you can run that off 2. Strongly urge you to run it off 3 if possible, because that doesn't apply. 3 wires, the sky is your limit. So we've got many options on 3 wires that you can do. So we've got all of our T-Series, our T6, our T10, our 9000 Smart, our Vision Pro 8000 Smart, as well as any of the ones that are listed to the left. So it's a nice reference if you get out on jobs, if you guys do service work and you're out on a job site and you find a wire that's busted, here's all the part numbers, well, not the part numbers, but here's the model numbers, and Jackson's got all this in stock. They can hook you up with everything. A little bit about the wiring. So I kind of hinted on this. I'm getting more and more calls because more and more people are starting to go to smart homes. It's just, if you haven't been getting those calls yet, they're coming. If you've got an existing system with 2 wires, I showed you some of the thermostats that would work. This is how you would do it. So in very small image down at the bottom, I've got a picture of our hydronic panel. This is our equipment interface module going to a Prestige. So this is one of the options for using 2 wires to get onto a connected system. So those 2 wires across the top that are marked R and C, all that's doing is literally throwing power to the thermostat. Those other 3 wires that you see there, C, R, and W, that's what's basically making the call to the hydronic panel, and that's what's powering up the board as well. We have a question, yes?
Yep. Constantino wants to know, is Honeywell Homes Residio still making the Focus Pro thermostat?
We had to talk about that earlier, didn't we? We make the Focus Pro 1000. I think it's just called Pro 1000. Short answer, no. I'll leave that as a short answer. Check with Jackson Systems.
All right.
So the T series was developed to replace the Focus Pro series, is really what it is. So we're not going to be manufacturing them moving forward, but with that being said, check with Jackson Systems. Yeah.
Way to toss that back at us.
That's right. And then Vision Pro. So this is the exact same wiring diagram. The only difference here is you don't see the R and C. This is your totally wireless option here. So still hooks up to the hydronic panel. All your wiring in the mechanical room and your operation of how that works is exactly the same. The other thing, and I threw this in here more or less for reference, the next 2 slides. So the first one is showing you what do you do if you've got 2 stages of heat. So let's say your first stage of heat is radiant and your second stage of heat is a furnace or a baseboard or a fan coil unit or whatever you could dream up. This is 2 different ways you can do it. These are described in much more detail in our wiring diagram reference guide that we've put together. But depending on what is the secondary stage of heat, there's different ways to wire it up. Both of these applications require a relay, but these are simplistic relays and the wiring is pretty straightforward. If you do run into, one thing I will touch on is if you do get into a home where you have 2 stages of heat and you want the radiant to be first stage, if it's in-floor radiant heating, there's a lot of mass in the ground. It takes a long time to bring that mass up to temperature. I mean, if it's a slab, it could take multiple hours to bring the temperature to where you need for the thermostat. The problem with a lot of our 2-stage thermostats is it will try the radiant heating first, but even with the programming settings, a lot of times you can't give it enough time to bring that slab up. Our Prestige thermostat, just going back, is the high-definition color display. That thermostat has the capabilities of programming anything you can dream into it for setting up the radiant heating. So you can set up minimum temperatures, delay times, etc. You dream it up, it's in there. If you have a high-end luxury house where they're using radiant heating as a primary stage of heat and they've got forced air for backup, I strongly recommend taking a look at our Prestige because you've got the ability to really program it, because people buy the in-floor radiant heating for the luxury aspect. They think that there's a misconception they're always going to have warm floors, which is not always the case, but they at least want that radiant feeling. If you put in a standard 2-stage thermostat, we can make it work, but it's going to come, the forced air is going to come on way too often. And then kind of throwing everything together, I've got a T775 that we talked about with 2 boilers wired into one of our hydronic panels. So kind of tying everything together at the very end. Again, they'll have this as a reference in a PDF so you can look at it to see how to do it, but it's kind of hooking everything together. With that being said, I'm going to pause for a minute to see if we have any questions.
All right. Well, I appreciate it very much, Chris. Thank you for coming out this evening and giving us an incredible education on all the cool products from the new Residio and so forth. We're really excited Jackson Systems offering all these products now. So please give us a call. Of course, we'll be posting the video on demand. So if you want to watch it sometime in the future, feel free to jump on jacksonsystems.com. You can watch that, stop it, and check out some of the wiring diagrams. And if you do need any of the support material Chris talked about tonight, let us know. We'd be happy to email it to you or send it to you. And with that, thanks again for joining us tonight at Jackson Systems live training. Thanks a lot.
Thank you.
Appreciate it.